Today we are starting a new unit. We're going to be actually combining or talking about solutions and acids and bases this unit. And we're going to start off talking about intermolecular forces and physical properties. Because if we're talking about solutions, we need to know what kind of things will dissolve in water to make solutions and why things are dissolving in water. So to do that, we're going to look at intermolecular forces. And when we talk about intermolecular forces, that inter, I-N-T-E-R, not R-A, inter, refers to the forces between molecules. Okay, so these will determine physical properties of substances. This is not to be confused with intramolecular, which would be forces within a molecule, and that would deal more with the chemical properties. But this is forces between molecules and how those molecules are interacting with each other. To give substances the physical properties that they have. And we're going to look specifically at water because it is very important to life on Earth and to chemistry. So let's start with the first kind of force, of intermolecular force, and we call these IMFs. IMF. So we're going to look at dispersion forces. Now, dispersion forces are weak forces, all right? So we're going to talk about some stronger forces. These are weak forces. And they result because electrons are always in motion, right? They're moving around. And even though this is typical for non-polar molecules, even though the electrons are evenly distributed, they will move around and they'll cause temporary poles to form, okay? I said this is important for non-polar molecules. This is also an important force for non-metals, diatomics specifically, and noble gases. So remember our diatomics, H2, F2, N2, O2, you know the rest. All right, so diatomics, noble gases, and nonpolar molecules where we have carbon and hydrogen bonding, okay? Our example up here, C2H6, all right? If we had time in class, you already drew this Lewis structure, C2H6. Notice that there's no lone pairs of electrons. This is a non-polar molecule, right? It is a mirror image up and down, left and right. Remember we talked about that. All right, so non-polar, those electrons will move around, form temporary poles, and dispersion forces are the main forces in play here with molecules of C2H6 interacting with each other, okay? Our second force is dipole forces. Now, hopefully you see dipole, all right? So we're going to have two poles forming, all right? We are going to have oppositely charged particles or oppositely charged regions on dipoles, okay? These oppositely charged regions are going to be attracted to each other. Positive attracts negative, negative attracts positive, okay? So we're going to have oppositely charged particles, and hopefully you're thinking that must mean it's a polar molecule, because if it's nonpolar, there's really no oppositely charged regions that aren't more than temporary, okay? So this is an important force for polar molecules because polar molecules are not sharing electrons evenly. In the case of HCl here, hydrogen has given up its electron, or has not given up, but it's sharing its electron here with chlorine to make both of them feel like they have a full octet, hydrogen with 2 electrons in its valence, chlorine with 8 electrons in its valence. But chlorine is slightly more negative here. It's pulling the electrons towards it. Hydrogen is slightly more positive, okay? So we have 2 poles, positive and a negative. Oftentimes we'll indicate that with negative and positive, okay? All right, now, the third type of force that we have is a pretty strong force. This is hydrogen bonds. These are very attractive forces, but they're only between molecules that have, you guessed it, hydrogen, okay? They have to have hydrogen, and that hydrogen is bonded typically to very electronegative atoms, okay? Now remember, electronegative means that they really want electrons, they're really attracted to electrons. As we looked at the trends for electronegativity on the periodic table increases up and to the right, making fluorine our most electronegative atom, okay? So hydrogen bonds will be between hydrogen and electronegative atoms like fluorine, oxygen, and nitrogen, okay? The most common example, if you can think of hydrogen bonding with oxygen, is water, okay? we have two hydrogens bonded to an oxygen. This is also a polar molecule, right? That oxygen is pulling the electron. So the oxygen is more negative. These hydrogens are more positive, okay? But the main force at play here is not dipole forces because hydrogen bonds are so strong. They're very attractive forces. So the main forces at play here are hydrogen bonds, okay? Now, hydrogen bonds are extremely important in determining properties of different substances, water being the big one that we talk about, but also things like DNA and proteins, all right? And that's because we have hydrogens being attracted to electronegative atoms, okay? So, in determining the properties of water, hydrogen bonds are responsible for all of these properties of water that we've talked about at some point or another. The freezing or melting point of water being 0 degrees Celsius, the boiling point, remember vaporization or condensation point, being 100 degrees Celsius. Having relatively high specific heat, remember we compared the specific heat of the water in the pool to the concrete or the cement outside the pool. Water takes a lot more energy to heat up, okay? So, relatively high specific heat. It has high surface tension. Think about the difference between maybe diving into a pool versus belly flopping into a pool, right? Water has very high surface tension, so that belly flop is going to hurt, okay? And the last, or not the last one, second to last one that we have here is the density of water. If you put ice in water, what happens? Ice floats. So, the physical property of ice being less dense than water is also determined by these hydrogen bonds. Next board, or the third board, we're going to be talking about one of the biggest physical properties, and that is solubility of things in water. So those hydrogen bonds determine what is soluble in water and what is not. Okay. Now, the very last force that we're going to talk about, all of those were for covalent compounds, molecules. The very last IMF we're going to talk about is the only one that exists for ionic bonds, or that's prevalent for ionic bonds, or important. And that's just the electrostatic attraction, right, between metal cation and nonmetal anion. The most common one we talk about is NaCl. We have Na giving up its electron to chlorine, making sodium have a +1 charge and chlorine have a -1 charge. This is an ionic compound. The opposite charges are then going to attract, right? So here's some examples. We're going to identify our 4 IMFs at work here. So I have CaCl2. Here's the Lewis structure for CaCl2. What kind of compound is this? Hopefully you know. This is an ionic compound, okay? If this is an ionic compound, then the IMF at play here are ionic bonds, okay? Our second one over here, HF, H bonded to F, right? They're sharing electrons. This is a covalent compound. This is a molecule, all right? And we see that we have a hydrogen bonded to a very electronegative atom, fluorine. So this is, we have a polar molecule here, but the IMF that is most at play has to be that very strong force of hydrogen bonds, okay? And I should put up here, this is a covalent compound, okay? Now, our one down here, CH4, we have carbon, 4 hydrogens around it. There are no lone pairs of electrons. The electrons are being shared evenly, more or less, all right? There will be periodic temporary poles that form when electrons are moving. So this is going to be, first of all, we have C bonded to H. This is covalent. Mirror image, so this is nonpolar. And the force that's really prevalent or important here is dispersion forces. Okay. Now our last one over here, carbon bonded to oxygen. It's a triple bond between the two. We see that both of them have a lone pair on them. Sorry, both of them have a lone pair on them. But the oxygen is going to be slightly more negative. It's going to pull the electrons slightly more toward it, right? The carbon is slightly more positive. That makes this one, we see carbon and oxygen bonded. This is covalent bond. They're sharing electrons, right? And we have dipole forces present here, right? Because they're going to be, one side is going to be slightly more negative, one side is going to be slightly more positive, and that's because of the electronegativity of carbon and oxygen. Oxygen is a more electronegative atom, and so it pulls the electron. It attracts the electron more strongly to it, so it's going to be slightly more negative, carbon slightly more positive, right? Now, those are all the forces and the physical properties that are taking place, right? The forces that are causing these physical properties. Let's take a look at one of the physical properties, and that is solubility. Okay, so in aqueous solutions, what is happening? Right? Now, remember that solutions refers to a homogeneous mixture. That means it's the same throughout. And aqueous solutions are composed of a solvent and a solute. The solvent dissolves the solute. The most common solvent we really see is water, okay? So, one of the things I think you've heard me say in class, but I don't know if you remember, is that like dissolves like. And we talk about this in terms of water, because water is a polar molecule. If like dissolves like, then a polar molecule, water, dissolves any other polar molecule, okay? So, because water is polar, other polar molecules will dissolve in it. So to figure out if something's going to dissolve in water, all we have to do is determine if it's polar or nonpolar, okay? That's one little bit of it. We'll see the other bit in a sec, right here. Actually, I'm going to start with this middle one. Okay, so we have C12H22O11. This is table sugar, all right? This, you don't necessarily have to draw this out. You'll see structures like this when you get to organic chemistry in college if you take organic chemistry in college, all right? What we have here is... we have a nonpolar, okay? So this is table sugar, right? It doesn't, sorry, not nonpolar. This is polar, right? Notice that it might look like mirror image, but this actually has 6 little sides here. This little piece right here has only 5, okay? So it's not actually a mirror image. It looks very complicated. You might think that it is a mirror image. It is not a mirror image. All right, so whether this is polar or nonpolar, I have it right here. This is polar, right? It's not a mirror image, so it's polar. What kind of IMFs are at play? Well, we have polar, so one side of the molecule is positive, one side is negative. It's going to attract the positive of another. The negative over here, right? So the opposite poles are kind of attracting each other here. When you put those in water, what happens is the hydrogen, which is more positive in water, is going to attract the negative pole. The oxygen of water molecules is going to attract the positive pole. So the hydrogen is going to pull the negative, the oxygen is going to pull the more positive, okay? These will not dissociate, right? So it's not like breaking up into ions, because there's no ions to break up into. Not dissociating, but we know that this is polar, and we see a lot of oxygens bonded to hydrogen. That means that our IMF that's at play here is hydrogen bonds, okay? Will this dissolve in water? It's polar, so yes, it is soluble. All right, if we take a look at our one over here, this is baby oil. Notice I'm not drawing this out because C54H100O6 is not going to be fun to draw, okay? But is this polar or non-polar? I'm not going to show you the structure because it'll take too long to draw. This is actually a non-polar molecule, okay? The IMF at play here for non-polar molecules is dispersion forces. And will this dissolve in water? You know that oil sits on top of water. No, this is insoluble. Right? Now the last one is an ionic compound, NaCl. So I include this here. Ionic compounds also dissolve in water because they dissociate. So we have a polar molecule, right? This is ionic, right? It's not a covalent compound, so it's not polar or non-polar. The IMF at play is ionic bonds. And yes, this will dissolve in water because it'll break them to its ions.